Okay, so let's begin with couple of examples going back to the application of constraint relations that we learned in Newton's laws earlier, but we will also include friction in these examples now. So we have a situation like this. We have an inclined plane. And this surface is rough now. So theta is, let us say, 30 degrees. Mass of this block is 20 kilograms, and the coefficient of friction is 1/√3. Okay. So the first thing is we have to find the minimum and maximum possible value of M2 such that the system is in equilibrium. So this is a standard type of problem, so you'll have to take into account that the pulleys are massless and smooth. Okay. So this is a rough surface which is having a coefficient of friction mu. So find the minimum and maximum possible mass M2 such that the system remains in equilibrium. Okay. And next up, we will also find the accelerations of the two blocks. If M2 is equal to 70 kilograms instead. Okay, so just start with the free body diagrams and the equilibrium condition over here. Okay, you'll understand that because it's a rough surface, so depending on the tendency of slipping, whether M2 is comparatively lighter, so the tendency of slipping is for M1 to come down the inclined plane, or M2 is comparatively heavier, so the tendency for M2 is to slip up the inclined plane. So accordingly, friction can act in either direction. Friction can be acting down the inclined plane or up the inclined plane. And for the limiting condition of these two types of friction, we'll get the limiting values of mass, the minimum and maximum value of M2. Okay, so let's start with the relevant free body diagrams.
So once again,
Yeah, you go ahead and solve it. So for the condition where So if minimum mass condition is being applied, then the tendency for slipping is in the backward direction. So friction should be acting up the inclined plane. And on the other side, for the free body diagram of this block, there will be a tension of 3T acting upwards.
Sir, are we not considering mg sin theta?
Mg sin theta is a component of mg beta. It's there in the diagram. The weight vector has two components, cos theta and sin theta component, which you can see within the vector diagram. So we are considering this object to be at rest, okay, because minimum mass M2 is placed over here. Condition for minimum value of M2 keep the system in equilibrium. Is that limiting friction mu n1 or whatever mu n acts up the incline on M1. So for M1, you can see the free body diagram equations are that T plus mu n balances the weight sine component. Okay, this angle is theta. And n balances the weight's cos component. And for this one, the condition is that for M2, the condition is that the weight is balanced by 3T. Okay, because as you can see in the diagram, there's a combination of pulleys acting in such a way that a total of 3T tension is acting vertically upwards on this block.
So could you
On
please
M2.
explain it again? Like,
Free body diagram beta. See the forces which are acting on each of the blocks. Okay. So if the system is in equilibrium, each of the blocks should have net force 0. So the total tension force acting on the block M2 is 3T upwards. And there's only one other force, weight. So these two should balance. So that is this equation. Whereas the forces acting on the block M1, they are a combination of tension, weight, normal reaction, and also friction. Now we are applying the condition that the minimum mass M2 is keeping M1 at rest. That means the value of tension is comparatively less because M2 is comparatively less. So M1G sin theta here is dominating over tension. This is greater than tension because we are comparatively small, because we kept the mass M2 comparatively small. So that's why static friction acts opposite to mg sin theta. M1G sin theta के opposite act करेगा. And when that static friction is equal to the limiting value mu n, then we have the condition for M2 to be minimum. Okay. For the minimum value of M2, we have the condition that the limiting friction, that is the maximum possible value of friction mu n, acts up the inclined plane. Is it clear now?
yes, sir.
Okay. We will just use a slightly different value of mu over here because we want mu to be less than tan theta. Okay, and theta is 30 degrees. So we'll use 1 by 2 root 3. Instead of 1 by root 3, we'll use the value 1 by 2 root 3. So just take a corrected value of this. Okay. Anyhow, so solving this system of equations, now you can see that substitute that over here. So you'll get and from here you substitute T's value as 1/3 of M2G. So that will give you the condition that this is the minimum value. The system in equilibrium. Now, similarly, your voice is echoing, but I'm not able to hear. Can you send me a text message, please?
Sir, the minimum value comes to 0, no?
0 if you have taken mu as 1 by root 3. You've done that?
Yes, sir.
Yeah, it is correct. Okay. But
Yes, sir, and I was getting that only, but I thought it was wrong, so I cancelled it.
Okay. No, it's not wrong. For mu equal to 1 by root 3, the correct answer is actually 0. Even if you don't hang any mass from that side, because mu is equal to tan theta, na? So on the basis of friction alone, M1 will get balanced. That's the minimum value, though not the maximum value. Okay. But for your benefit, what I've done here is I've adjusted the value of mu. Instead of tan theta, I've taken it as half of tan theta now. So take this new value of mu and you will see you'll get a non-zero value of this minimum. So substitute these values now.
Okay, sir.
If you take mu as 1 by root 3, the correct answer is 0. There's nothing wrong with the answer 0. Okay. And you can understand why that is the case, because the friction alone is balancing mg sine theta for that block. So we don't need tension in the string. So we don't need mass on the other side. Even zero mass, no mass balance from the other side will keep the system in equilibrium. Anyhow, so the mass of this block is how much now? It's 20 kg, isn't it? Yeah, so 20, theta is 30, and mu I have taken as 1 by 2 root 3. So sine 30 minus 1 by 2 root 3 times cos 30.
Sir, with mu is equals to 1 by 3, I got the value as 60 kilos for maximum.
Mu equal to how much?
60 kilos.
Actually, you got a 60 kilos. No, but it will be more
Yes,
than
sir,
60.
for maximum value. No, sir, I took 1 by root 3. That time it came 60.
So 1 by root 3. Yeah, that's correct. 60 kg. In this case, however, we'll get the minimum value as 15 kg, taking the value of mu as 1 by root 3. So this is the minimum. Okay, so all of you are following this. Now, how to change this minimum condition on M2 to the maximum condition? If the mass of M2 is
Sir,
comparatively
friction
larger,
will be reversed.
yes, the direction of friction will be reversed. And for the maximum case, take that reverse friction as the limiting value of friction. So take it as mu n. So yes, if you take mu as 1 by root 3, you will get 60 kg as the maximum. But here, don't forget to take the value of mu as 1 by 2 root 3. I have adjusted it to these values.
Sir, M2 comes out to be 45 kilos, sir.
45, is it? Yes, 15 into 3, that's correct. Because the friction will be how much? It will be 5 newtons and mg sine theta is 10 newtons. And mg sine theta is 100 and the friction is 15 newtons. So
Sir, how do we
tension has
get,
to be 1. Yeah, tell me, beta, how do we get?
sir, how do we get M2 as 15 kg? I got 30.
M2 as 15. See the calculation better na, sine 30 minus 1 by 2 root 3 cos 30 कितना होगा? Half minus 1 by 4. So 60 का 1/4 कितना होता है? It's 15 kg, is it not? Is this equation clear up to this point, beta? This one?
No, sir, like 60 into 1 upon 2 minus 1 upon 4. Then it becomes 30. Like that.
No, it's not, beta. 60 into 1 by 2 minus 1 by 4, do the algebra correctly, it's 15. Arey, half of 60 is 30 and 1/4 of 60 is 15, betas. Is it clear?
Okay, sir, got it. I made a calculation error. Never mind. Thank you, sir.
Okay, so let's understand the other one now. So the condition for M2 to be maximum but no slipping is that limiting friction is now acting down the inclined plane. For equilibrium is that limiting friction Okay, so this is our system of equations now. So we will get m2g by 3 equal to m1g sine theta plus mu cos theta.
So why do you equate like tension equals to mg sine theta plus frictional force? Like
Because
over
these
here,
are
the
test,
body is in motion.
it's balanced, na? The forces are balanced. So you have resolved the weight. The weight's components are m1g cos theta, m1g sine theta. Then from the other side, there's tension acting. Then there's normal reaction acting. But also this time you kept the mass of m2 comparatively heavier because you want to find the maximum. So tension is dominating over m1g sine theta. So friction acts upwards, up the incline, sorry, down the incline. Tension is dominating.
So
So
sir, if we want an acceleration, like that means the body is in motion. So like why to equate? There should be a greater than symbol, right?
have you read the condition beta? We don't want acceleration. The idea is we want the system to be in equilibrium. So when this reaches the limiting value, that's why we are talking about static friction, no? And that's why we are talking about limiting friction, because there is no slipping occurring.
Sorry, sir. Then I got confused with the question.
Understood? Maybe you saw the third part of the question where I've given the mass of m2 and I've asked you to find out the acceleration. But this is the second part of the question, or the first part, where we are calculating the condition on m2 so that there is no motion, so that the system is in equilibrium. Okay, clear now?
Yes, sir. Sorry, sir.
Okay, no problem. So this value of m2 that we are getting from here, this is going to give us the maximum possible value of m2 such that the system will not move. It will remain in equilibrium. Okay, so this value is the maximum value for equilibrium condition. So which means that if we, whatever we are calculating here, suppose in the next part the mass that I've given is greater than that, then definitely there will be acceleration. So this will give us m2 is 45 kg. So what we'll see, this is the maximum possible value. So in general, as long as m2 is not less than 15 and not greater than 45 kg, this is the condition for equilibrium. Now, for example, here, if suppose the mass m2 instead of 45 kg, it is 40 kg, it doesn't mean that there will be motion. There will still be equilibrium, but the friction acting on m1 will be less than the limiting value. A static friction of less than mu(n) will be acting on m1. Okay. Only if the mass exceeds 45 kg, or on the other hand, the mass is less than 15 kg, there will be acceleration. If the mass of m2 is more than 15 kg, then m2 will come down and m1 slip up the incline. And if the mass of m2 is less than 15 kg, then it's vice versa. m1 will come sliding down the incline and it will pull m2 vertically upwards. Okay. So that is why in the next part of the question, I have given you the mass m2 as 70 kg. So you can see it's now, it is not satisfying the equilibrium condition anymore. The moment we take m2 as 70 kg, it's not satisfying the equilibrium condition. So that means there will be slipping. So that's why I've asked you to calculate the acceleration in that part. So if m2 is now, instead of these limiting values, it's 70 kg. The rest of the things are the same. Find accelerations. These are still the same. So not only we know there will be acceleration, but we know the direction of acceleration. m2 will be coming vertically down and m1 will be slipping up the incline. But now the moment there is motion, don't forget that there's a system of pulleys. So you'll have to take into account that there's a constraint relation between their accelerations. Okay. So first of all, people, can you tell me what is the constraint relation? What is the relationship between A1 and A2? A1 being the acceleration of the block M1 up the inclined plane.
Sir, A1 is equals to 3A2.
Yes, very good. That is correct. So that will be the constraint relation. Okay. Because of the thread length conservation principle, you can see that if M2 comes down by a certain distance, like say X, then it is pulling 3X amount of thread. So the displacement of M1 will become 3X. The displacement of M2 is X. So accordingly, the relation between the accelerations will also be like that. So A1 is equal to 3A2. This is the constraint relation. It's coming from thread length conservation. Then you have the individual free body diagrams. So now kinetic friction will act because we've taken one single value of n mu. So that kinetic friction is also mu n. But otherwise it would have been mu k into n. So now this is not in equilibrium anymore. So there's a dynamic situation. So T minus mg sine theta minus that kinetic friction. That is the net force up the inclined plane. So this is M1 here. And Normal reaction is Bates cost component. And of course, we know that substitute this over here. So we will get the relation that T minus m1g sine theta minus mu m1g cos theta equal to m1 k1. So this becomes one equation for this. And on the other side, for the block M2, is going down with A2. So the net downward force is weight minus 3T. That's our second equation. Oh, sorry, that's our next equation. So in a sense, this is our third equation. The constraint relation we can write as a fourth equation. So actually we solved it first. So three equations from free body diagrams and one equation from the constraint relation. We are having that many unknowns, A1, A2, T and N, four unknowns, so four equations in all. Okay, so let's substitute the values in these two equations. So we get them numerically. So this equation will become T minus M1 is how much? 20. So 200 sine will become 100 minus this mu M1G cos theta become 1 by 2 root 3. Yes, into 200 into root 3 by 2. So this will be 50, is it?
Yes, sir.
Yes. Very good. So that should be equal to 20 A1. And in this one, we have 700 minus 3T should be equal to 70 A2. Now see, one easy way to eliminate the tension is we can multiply this whole equation by 3 and add these two equations. Okay, so this is just a tip for solving. So there is T here and there is minus 3T here. So just to eliminate the tension, do this. Okay, so we have 700 minus, this is actually 150 into 3. So 450 will become 60 because we multiplied this plus 70. Okay. And then we will substitute A1 as 3A2 from equation 4 above. Okay. So this will become 250 newtons is equal to 60 3A1 plus 70 A2. That's becoming how much now? 180 plus 70. Right, simplifying 250. So just check my solution, but I'm getting A2 as 1 meter per second square, which means that A1 should be 3 meters per second square.
Yes, sir. I'm getting the same.
Okay, good. Very good. Okay. So these type of questions can be, the slightly trickier questions at your competitive exam level, where concepts from friction, limiting friction, as well as constraint relation with system of pulleys is being put. Okay. So once again, conceptually, what we are doing is we are making the free body diagram, resolving the forces and writing the Newton's law equations. Net force is equal to mass into acceleration, okay, for the individual blocks M1 and M2. But that is not enough to complete this problem because they are not having the same magnitude of acceleration. So we need one additional equation which is not going to come from free body diagram or equations of motion. It's going to come from the constraint in the problem, which is that we have a system of pulleys such that the string has, three vertical sections which are indirectly attached to M2 and only one section that is attached to M1. So because of that 3:1 kind of ratio, what is happening is that the displacements of M2 and M1 are in 3:1 ratio. If M2 goes down by 1 centimeter, it will pull M1 up by 3 centimeters because it's pulling 3 centimeters of thread. So that constraint relation is the additional thing that we're using. So 3 equations we are getting from free body diagram, 1 equation from constraint relation, and then the rest is a matter of solving. Okay, so as you can see in these type of questions where you have more than 2 or 3 variables, solving can sometimes be like a lengthy process, tricky and lengthy process. So you have to just make sure that you practice enough questions so that you know how to handle the solving. It is just a function of practice, nothing else. Okay, it's not something difficult, but at the same time you have to keep doing it. All right, now the next type of problem we'll discuss in friction is going back to the 2-block problem that we were discussing last time. Towards the end of the lecture, we had discussed one 2-block problem. Now that is again a very typical type of problem, and today we will add to the complication in that. In the last session, we had seen a 2-block problem where there was friction in only one contact surface, that is the contact surface between the blocks. Today we'll see a situation where there's friction at both the surfaces, the ground as well as that one. Okay, so let's see what I'm talking about. So this is now a rough horizontal surface. It's not a smooth surface in this problem. And on top of that, I have kept a block which also has a rough surface. And on top of that block, I've kept another block. So there is friction between the two blocks. And there is friction between the ground and this one. So this is also a rough surface. This is also a rough surface. And in this example, let's say this is mass M1, this is mass M2. This is having coefficient of friction mu1, this surface. And this surface is having coefficient of friction mu2. And now the system is initially at rest when we start applying a force F. So let's take some values. So find the accelerations of M1 and M2 if a force F is applied horizontally to the lower block M2. The first part will take the magnitude of F as 15 newtons. The third case, we'll take the magnitude as 40 meters. Should I quickly just review the problem solving method that we had taken last time when we had seen the 2-block problem, but without the ground being rough. Okay, so there was only mu1, the ground below, which we have taken of coefficient of friction mu2 over here. In that case, that was having no friction. It was a smooth surface. But we had sort of developed a way of visualizing the problem and understanding how to look at the condition when there is slipping versus the condition when there is no slipping. So let's try to apply that same method and same type of logic over here also. Okay, so let me check the answers that I have got. Yes, very good, Sanvi. Correct for the first case. Yes, Rishita, correct. Very good. For both blocks. Yes, that's correct. Okay, so for the first part, your answer that both blocks should have zero acceleration. That is, both should remain at rest. I'll explain this in a minute, but if you have finished this first part, you can go on to the second part. Find out what's happening when the force is 25 newtons. Okay, so let's just start this by visualizing the free body diagrams. Upper block, the lower block. Okay. Now, so these are the vertical forces. So these are the two normal reactions. Okay. So now what happens is that the moment we apply a force in this direction on the lower block, it has a tendency to slip towards the right. So the first thing that happens is that a friction sets up acting over here. Okay. So now we can see that F2's static friction's maximum value is such that it is less than equal to mu2 n2. So F2's maximum possible value, you'll see from above here, it is 20 newtons. So that means that if F is less than equal to this maximum value, then F is balanced by F2 and M2 does not have a tendency to slip because the ground only balances the external force F. So there is no friction that acts between the two blocks. So A2 becomes 0 and no friction acts between M1 and M2. Okay, so that is something we straight away know, that we need to apply a force of more than 20 newtons to even give that block M2 a tendency to move, let alone. Okay. Now we can see that on the other hand, if we do give it a force of more
Sir,
than,
for the lower block to move, there should be more than 15 newtons, no?
नहीं बेटा, लिमिटिंग फ्रिक्शन देखो कितना है वहां पे, it is mu2 into n2 ना, and mu2 was 0.4. Okay.
Okay,
Now
sir.
what
Okay, sir.
happens? Now what happens if our f is now greater than this? Just so what happens if the force that we are applying is greater than F2's limiting value? That is, F is greater than 20 newtons. Then what will happen is M2 tends to slip. Okay. So therefore, friction F1 between M1 and M2 starts acting. So now there is a friction like this which will act. Okay. Now this friction, sorry, this is F1 only. There will be a friction F1 that will act in this case. Okay, for the case where F is greater than mu2 and 2, or F is greater than 20. This case it will look like this. Okay. So this friction F1 will try to prevent slipping between M1 and M2, such that A1 should be equal to A2, but they are non-zero. And in this case, F2 will be a kinetic friction. Because slipping is happening with respect to the ground. Now the question is whether slipping is happening between the two blocks or not. So if A1 is equal to A2, then friction F1 is a static friction between them, and it's less than equal to mu1 N1. On the other hand, if that is not the case, then there is slipping between them. Yeah, so I've got some more answers now. Rishita, see what is happening in the second part. If you go through what I've explained just now, once your force is more than 20 newtons, okay, slipping is happening with respect to the ground. So it cannot be that your lower block will be at rest. Okay, but there is friction between the two blocks now. And what that friction F1 is trying to do, it's trying to prevent slipping between them. So what is the priority for that friction? That E1 should be equal to E2. It's not that they should be at rest. That's not possible here now. The moment your F is greater than 20 newtons, the blocks cannot be at rest. Either they are both moving with separate acceleration with slipping between them, or they are moving with common acceleration and static friction acts between them.
Yes, sir. I understood that. Like after
Understood, right?
explained
Yeah.
it.
Okay. So now try and see again what is happening in the case of the second part where I've taken the force to be how much? 25 newtons. Okay.
Yes, sir. I'm trying.
Khushi, you also try to check your answer once more, beta. Because see, again, in your answer, what is happening? A1 is different than A2 in such a way that A1 is moving faster than A2. I think that's not logical. No? You are applying the force on the lower block. How will the upper block start moving faster? Friction will prevent slipping between them. No? It's not creating slipping between them. Understood the point? No? So in that case, mostly what is happening, the friction F1 that is acting is a static friction. So it is less than 4 newtons. It's not equal to 4 newtons. Okay, so second part, what is the acceleration coming out now, people? Rishita, you're getting 3, is it? Let me do the question.
Actually, I'm not. I don't think I'm able to figure out the direction of one.
Okay, I'll explain. Okay, so see, these two FBDs are clear now in this diagram that I made. Okay,
Yes.
why the friction's directions are like this? This is clear now.
Yes, sir. This one is clear.
Okay, so now see, this will be the situation whenever my force is greater than 25 newton, than 20 newtons. Okay, the moment the force is greater than 20 newtons, the individual FBDs will look like this. Okay, whereas if the force is less than 20 newtons, then there won't be any F1. Okay, then what will happen is that this thing only will balance it. F2 only will balance the
Yeah.
external force. Okay. Now, so let's apply it now. Okay, so on the other hand, here if I take a situation where F is less than 20 newtons, then this F1 and F1 won't be there, and both these accelerations will be 0. So here if F is less than mu2 n2, or F is less than 20 newtons, okay, then whereas here E1 will not be 0, E2 will not be 0 the moment F is greater than 20 newtons. Now there can be two situations possible. Slipping between M1 and M2, and no slipping between M1 and M2. These are the two possibilities, right? So
Yes.
if this, yes, so if there's slipping between M1 and M2, it means that E1 is not equal to E2. Okay, and the friction F1 that is acting, that is a kinetic friction. So it is equal to mu1 n1, or it is equal to 4 newtons. Okay, whereas if there's no slipping, that means A1 is equal to A2. It's not unequal, and the friction that is acting, that is a static, so it is less than equal to, it can be less than mu1 n1 also. So friction can be less than equal to 4 newtons, but the condition is that A1 must be equal to A2 if there is no slipping. Okay, so the moment my force is more than 20 newtons, now I know that this possibility is not there, that A is 0. There are only these two possibilities, that either A1 and A2 are equal but non-zero, or they are unequal and at the same time non-zero. Okay, so for 25 newtons, as well as the next part where I have taken third part, kitna liya hai force? I think I have taken it as 70 newtons, is it, or 40 newtons? Okay,
40
so
newtons.
both these parts, so both these parts we have to start with this situation here, that either there is slipping or there is no slipping, but A1 and A2 are non-zero. So normally when we are not sure whether or not there is slipping, what is the easy method we had discussed to solve the problem? We start with the assumption that there is no slipping. I mean, no slipping between M1 and M2. And for that, we find out how much friction is required. Okay, and we check that against the friction available, which is 4 newtons. Okay, so when we come to this part and we take F is 25 newtons, we know that the blocks must move. The question is how they will move. Okay, so now let's take the assumption, assuming no slipping. That is A1 is equal to A2, and that's non-zero of course, and F1 is less than equal to mu1 N1, or F1 should be less than equal to 4 newtons because it is a static friction. So with that assumption, what will the individual FBDs look like? Let's understand that. So I have applied the external horizontal force of 25 newtons on this. Okay, immediately slipping is starting, so this is a kinetic friction, which is mu2 N2, which I had seen was 20 newtons. Okay, but now I'm going with the assumption that there is no slipping. So if there's no slipping, then here this is which type of friction? This is a static friction. And here this is which type of friction? This is a static friction. And they are having a common acceleration E. Okay, this is clear now. The FBDs are clear. Okay, we'll just assume that they have some common acceleration. A1 is equal to A2 equal to some A, suppose. Okay, so now let's solve this. Okay, so we have for the block M1, we have F1 is equal to M1A, and for the block M2, we have capital F minus F1 minus F2 is equal to M2A. So these equations will numerically become like this, that F1 is equal to 2A and 25 minus F1 minus 20 is equal to 3A. Are these equations correct?
Yes, sir.
So F1 is 2A and 5 minus F1 is 3A. So now solving these, you can see that 5 is equal to 2 plus 3, that's 5A. So if they have a common acceleration, that's supposed to be 1 meter per second square. Okay, but now we have to check friction, whether this is possible or not. And the friction needed for this is how much? 2 newtons of friction is required. Now we know that F1's maximum possible value was how much? 4 newtons. So that means this thing. So this is the priority. Now friction tries to keep A1 equal to A2. But for doing that, how much friction is required? Only 2 newtons is required. How much friction is available? Up to 4 newtons is available. So that means the assumption is correct now, that there won't be slipping.
So in such questions, we should always go with the assumption that there is no slipping.
Yes, because see, if you go with the assumption that there is no slipping, you will either get the value of friction less than 4 newtons, like in this case, less than the limiting value, in which case your assumption is correct, or you will get the value of friction more than that and your assumption is wrong. So you can always go back to the second case, that A1 is not equal to A2, but the friction is kinetic friction. But if you start with the assumption that there is slipping, then you can get a very weird kind of result, strange kind of result, that you might get that A1 is greater than A2. Now imagine what that means, that the upper block is moving faster than the lower block, but actually you are applying force externally on the lower block. So that will be something that will not make sense and might confuse you at that stage. So it's better to start with the assumption that there is no slipping and then check whether you have enough friction for that. Okay.
Yes, sir.
So this is showing us that our assumption is correct. So assumption is right, and in this case F1 will be only 4 newtons, sorry, only 2 newtons. And A1 will be equal to A2, which will be 1 meter per second. Okay. Now the same pattern of solving I want you to follow for the third part, where we are increasing the force now further, and we are increasing it to how much? We are increasing it to 40 newtons. Okay. So this part now we are increasing the force to 40 newtons. So again, the only thing you can look at 40 and say that there is motion. You cannot directly say that, okay, is the motion happening with slipping or without slipping between the two? But because it's greater than 20 newtons, so you're overcoming the friction at the ground. So you know that both the blocks have to move. The question is whether they are moving with slipping or without slipping. So start with the assumption that they are moving together without slipping and check on how much friction is required. If it is satisfied, then your assumption is correct. If not, then you have to reverse the assumption and just make the adjustment to your free body diagram and you'll get the answer with that. Okay, so these questions take a bit of extra time because you have to do that trial and error kind of method, but this is the standard way of solving them. Okay, so let's see what's happening in this part now. When we are applying the force of 40 newtons, you see that if you start with the assumption that they are having common acceleration, probably see that there is slipping between them. Let me verify. So again, I'll go with that assumption.
Sir, there is slipping between them.
There will be slipping, right? So, but if I start with the wrong assumption also, I'll show you how you can correct your step. Even so, I'm deliberately taking the wrong assumption, assuming no slipping between the two blocks. Okay, so I'm taking A1 is equal to A2 equal to some common acceleration there. So F1 should be a static friction. So F1 should be less than equal to 4 newtons. This is a condition for no slip. So now, with that assumption in mind, my free body diagram will look something like this. F of 40. So on the ground, there is kinetic friction of 20 newtons. But here I am assuming there is static friction. Which is giving both of these presumably a common acceleration of E. So I have F1 is equal to M1A. And I have F minus F1 minus F2 is equal to M2A. So again, from equation 1 I have, from equation 2 I have this time 40 minus F1 minus 20 is equal to 3A, or 20 minus F1 is 3A. So when I compare these two, I get 20 is equal to 2 plus 3A. So if they had a common acceleration, that is as much as 4 meters per second square. But the required friction you will see is too much for this. And F1, which is 8 newtons. Now we know that F1's maximum possible value, which is mu1 n1, is only 4 newtons. So the moment I see this, I understand that, okay, my assumption is failed. So therefore, the assumption of no slipping, that is A1 is equal to A2, is incorrect. So that means A1 is not equal to A2 and F1 is a kinetic friction. So it cannot be less than, it is equal to mu1 and 1, equal to 4 newtons. So all I need to do is adjust the forces in my free body diagrams. Understand that these two are now kinetic frictions. So they have definite value of 4 newtons.
Sir, and after applying in both the equations 1 and 2, we get the value of acceleration differently, no?
Minute. Yes. Okay. So for the block M1, we have whereas for the second block, we have 40 minus 4 minus 20 is equal to 3 E2. So E2 is coming out to be how much? 16 by 3. Okay, so these are the accelerations according to me. You can just check out the values once, but the method is going to be this only for this type of situation.
Yes, sir. I got same for A2.
Okay, good. All right, people. So hope this question is also clear. I mean, this part of the question is also clear. Now, next up, let's look at another problem where, if you remember the concept of non-inertial frame and pseudo force we had seen in Newton's laws, that will come into play, but in a situation where there's also friction. So let's get some practice with something which combines both these concepts from this section. Okay, so in this example, what we have is an inclined plane like this. So this is at an inclination of theta equal to 37 degrees. And this surface is smooth. But on this now we have kept a block, or rather like a triangular wedge, which can slip freely. We have kept a 90-degree angle triangular wedge or prism kind of object. So it can slip freely on this. This one is of mass m1, but this surface is now rough. And on top of this, we have kept block. M2 like this. So if this surface has a coefficient of friction mu, so given that these masses are 10 kg and 5 kg respectively, theta is 37 degrees, g is 10 meters per second square. Now this mu is unknown. So first part is find the minimum value of mu if m2 does not slip with respect to m1. That is, this block remains at the same point on m1 as it slips down. Find the accelerations of M1 and M2 with respect to M1's frame if mu is 0.1. The coefficient of friction is, instead of finding the limiting value, the first part, if its value is given to us as 0.1, then what is the acceleration of M1 and what is the acceleration of M2 with respect to M1 or in M1's frame? So I'll give you the hint here. In the first part, what we have to do is you have to find the condition that M2 is not slipping. No? So that means when you look at M2's FPD in the frame of M1, it should be in equilibrium. But while that is happening, M1 is sliding down the inclined plane because there's no friction on the inclined plane. So M1 becomes which type of frame? It becomes a non-inertial frame. So when you consider the free body diagram of M2 in M1's frame, you must make sure that you remember to add the pseudo force correctly because M1 is a non-inertial frame. Exactly, Rishita. For both parts, now we'll consider M1's frame only. Okay. But the difference is in the first part, M2 is at rest with respect to M1. Okay. So it's a pretty simple situation in that regard. Okay. So let us assume that this thing, it is going down the inclined plane with some acceleration E. Okay. And this is at rest with respect to M1. Okay. So then one thing I can do is I can make M2's free body diagram in the non-inertial frame of the wedge M1. So that in a non-inertial frame is accelerating like this at E at an angle theta to the horizontal. So this will experience a pseudo force which will be opposite to the acceleration in direction. This is a pseudo force. And then of course it has its weight, it has some normal reaction. And to prevent it from slipping in this frame, it will be static friction acting like this. Because in this frame it is at rest. See that this angle is theta. So we have n plus m2a is equal to, sorry, n plus m2a is sine component is equal to m2g. And we have static friction is equal to m2a cos theta. Okay. Now for the second thing, what we can do is we can even easier is make a combined FBD of the wedge plus the block in the inertial ground frame. And this system is coming down with the acceleration A in this frame because the forces acting on it are the combined weight and some normal reaction, let's say n naught like this. So we have m1 plus m2 g sine theta is equal to this combined mass into acceleration. And n naught balances the combined weights cost component. So now substituting the values, you can see that from equation 1, we have, or rather, let's start with equation 3. From equation 3, we have is equal to g sine theta. So 6 meters per second square. Ten and 5 kgs. Now from equation 1, n plus five into 6 into sine 37, which is 3 by 5, is equal to 50. So the normal reaction here is equal to 50 minus 18 or 32 newtons. And from equation 2, we have the static friction acting on this one. static friction is equal to 24 newtons. So from this we will know the limiting condition on coefficient of friction, because the required static friction should be less than equal to mu n. So 24 should be less than equal to 32 mu. So mu should be greater than equal to we need a coefficient of friction of at least 0.75. Okay. So I'd like you to go through this very carefully when you're revising today's lecture. And since we're out of time, we'll discuss the second part of the question. The next lecture, I'd like you to try it out. Okay. And also finish maximum problems from friction from at least H.C. Verma this week. Next week, we'll be starting with the chapter work power energy, which is the next one after this.
Okay, sir.
Sir, in the next lecture, can you also explain this some once more?
Okay, go through this once more. I'll send you the notes and the recording, and we'll discuss the second part. And if required, we'll discuss the. I'll explain the first part once more. Okay.
Okay, sir.
Okay,
Thank you
that's
so
it
much, sir.
for this session, people. Yeah.
Thank you, sir.
Okay, beta. Okay, people. Bye.